If you ever played Assassin's Creed Valhalla, you've surely used Odin's sight. When I first used it, I was immediately hooked. It just felt so satisfying to use it. But have you ever wondered why this effect feels so good and what makes it so irresistible that you just feel like spamming it over and over again? Well, I did. I had to figure out what makes it feel so rewarding. And since I've already made something similar by recreating the terrain scan from Death Stranding, I figured, how hard could it be? Turns out, a lot harder than I thought. What started as a simple experiment turned into a full-blown obsession. Hours became days, days became weeks, and just when I was ready to give up, something unexpected happened. But I'm getting ahead of myself. Let's go back to where it all started. I started by manually modeling the whole Viking village by hand. Due to my extensive 3D modeling experience, it took only a couple of minutes. Then I gave birth to Adam and taught him how to walk around the environment. And with that, I had everything prepared to start working on the effect. Since I worked on a similar effect before, I already had a vision of how I'm going to approach this. I will implement it as a full-screen post-processing effect. Let's examine it to see what it consists of. Well, it seems like the effect starts about 1 or 2 meters away from the character and spreads outwards in all directions. The main part of the effect is a bright bluish color that is visible only in certain areas of the environment, which gives a feeling of some wavy pattern spreading everywhere. There's a lot more to it, but let's take it one step at a time. I quickly jumped back into Unity and started with the implementation of a distance mask. This mask will be used to provide the illusion of the effect spreading from the player outwards by limiting the visibility of the effect to a certain distance from the player. And here's the code that does just that. It calculates the world position of the pixel from its screen position and the camera's depth buffer. Then it uses that position to check the distance of the pixel from the origin of the effect. If the pixel is inside the current range of the effect, I will replace its color with a fully white color. And if the pixel is outside the current range of the effect, the original camera color will be displayed. Let's see how this looks. Okay, this seems to be working fine, but we're only showing a plain white color while the original effect displays a wavy, noisy pattern. This pattern is really interesting and it provides a unique feeling to the whole effect. I don't think the final effect would look as good if a different noise pattern were used, so I need to try to recreate it as closely as possible. For faster iteration, I started by creating a new shader graph that uses the simple noise node to visualize the noise pattern on a plane. Well, it would be way too easy if this noise pattern immediately resembled the original one, but we can still compare it and see where they differ. Well, the original pattern is way smoother than this one, which looks extremely random and like the values are not gradually changing between one another. Luckily, Unity has another noise node called the gradient noise. Let's see how this one looks. This noise isn't producing such sudden changes in value, it looks much more gradual and smoother. I can change some settings to tweak the scale and intensity of the noise, but I just couldn't get close enough to the original effect. After tweaking the values for a while, I got an interesting idea. What if the effect is not made from one noise, but from a combination of multiple ones? I quickly set up a graph that mixes multiple noise influences into the final noise value. Each noise function uses a slightly different intensity and scale. Of course, I can tweak these settings to get different results. And let's see how this looks. This is an interesting shape, but it still doesn't look like the original one. I tweaked these parameters for hours, but I wasn't getting anywhere near the desired look. Since I wasn't achieving a lot of progress, I decided to step back and research different noise functions. This led me across multiple interesting sites, like this one from Inigo Quiles, where he uses noise functions to create a realistic-looking terrain shape. However, understanding these noise functions requires a bit of advanced math knowledge since it relies on computing derivatives from cubic or quintic functions. Luckily, the sponsor of this video, Brilliant, will teach you the advanced linear algebra required for understanding these equations. Brilliant helps you get smarter every day with thousands of interactive lessons in math, science, programming, and AI. And what's special about these lessons is that they're designed to be uniquely effective by incorporating hands-on problem solving that lets you explore concepts on your own. This method is proven to be 6 times more effective than watching lecture videos. Personally, I use Brilliant whenever I need a quick refresher on math concepts that I haven't worked with in a while, which was exactly the case with computing derivatives from these functions. And for game development, you need a strong foundation in algebra, which with Brilliant's newly updated math courses is extremely easy to achieve. With visuals that bring core concepts to life, it's so much easier to develop your mathematical intuition, which is crucial for creating stunning visual effects for your games. So be sure to try out everything Brilliant has to offer with a free 30-day trial and 20% off an annual plan when you visit brilliant.org/gamedevbuddies or scan the QR code on the screen. You can also just click the link in the description. Thanks Brilliant for sponsoring this video. Now let's return to our hunt for the appropriate noise function. So while I was reading this interesting article from Inigo Quillas, I learned about fractional Brownian motions, which basically is just a way of combining multiple iterations of a noise function into a single coherent value. Within each iteration, you double the frequency of the noise while decreasing its intensity. This produces a soft, gradually changing noise that still contains a lot of detail. This looks like the solution for combining multiple noise functions which I was trying to invent earlier. You can find 2D examples of this on ShaderToy, which allows you to quickly test the different parameters and see how they affect the result. For example, this looks like something that is going in the right direction, so let's implement that in Unity. Since Unity doesn't support FBM out of the box in ShaderGraph, I need to implement it directly in the shader using HLSL. Luckily, Kjiro provided an HLSL noise library that can be downloaded as a package in Unity. Using the Perlin noise provided with the package, I implemented the fractional Brownian motion calculation. Unfortunately, the result wasn't appealing. Once again, I tweaked the parameters for a couple of hours, but I just couldn't get the result that would match the source. Damn, I was really hoping this would be the solution I was looking for. I feel like the fractional Brownian motion calculation is the correct path, it's just that the underlying noise functions aren't the ones I'm supposed to be using. I just can't believe that Unity doesn't come with some kind of noise editor out of the box. Well, after scouring the internet looking for different noise editors I could use, I stumbled upon this one. Wait, not this one. A built-in noise editor right inside Unity. What? It turns out that it exists. It's just contained inside the terrain package and not exposed as a separate package. Oh Unity, I will never doubt you again. Finally, armed with the visual noise authoring tool, I managed to get much closer to the original effect by using the Voronoi noise as the core noise function of the FBM. I mean, just look at these smooth value transitions and its wavy structure. I love it. And to test the look of this noise in the environment, I can just export it as a texture and sample it in the testing shader graph. Okay, this gives a slightly better insight into the final look, and while I like the look of the noise, it seems like the original effect is a bit more complex. Like there's a separate layer of noise affecting the visibility of this noise. To mimic that, I've created another noise texture that will serve as a visibility guide and updated the shader graph to read the values from the overlay noise texture and use it to alter the visibility of the original one. And after tweaking the values a bit, I got something that looks like this. This is looking quite similar in my opinion. Of course, one can always adjust these noise textures more to get an even better result, but this looks good enough for now. After implementing the logic for texture sampling into the original shader and multiplying the result with a specified color, we can see the current look of the effect. Nice. The shape of the noise is gradual and wavy, just the way I was hoping it would turn out. However, there's a problem. When the effect is shown across an area with buildings, we can see clear stretching in the noise pattern. This is happening because I'm using the X and Z components of the world position as the UV coordinates for sampling the noise texture, meaning that I completely disregard the height of the position. To tackle this, I need to use something called Triplanar Texturing to calculate the UV coordinates. The Triplanar Texturing technique calculates 3 sets of UV coordinates by combining pairs of individual components of the world position. So one set of UV coordinates would be the combination of X and Z components, while another would be the combination of X and Y components, and the third set is made of Z and Y components. Then we sample the texture 3 times using each set of UV coordinates. Finally, we add them together based on the normal vector to get the final result. I have a video explaining this technique in much more detail, so check that out if you're interested in learning more. And let's have a look at how this is looking now. Oh yeah, this is looking much better. The stretching is almost completely gone. Excellent. While the effect is looking pretty good, it's currently sampling both the base noise texture and the overlay noise texture using triplanar mapping, meaning that there are 6 texture samples in total for every pixel. However, we only need one value from each texture, meaning that we can combine these 2 textures into one by storing each noise texture into a single channel. The resulting texture will look a bit funky to humans, but the PC doesn't care. It's only interested in the data contained inside. I've used a free tool called Texture Merge for this. You can find the link in the description. And with that, we halved the number of required texture samples while still preserving the same look of the effect. That's what I'm talking about. I feel like getting the noise done right was the biggest obstacle for recreating the effect. However, there are still many things left to wrap it all up. Let's go back to analyzing the effect and see what's missing. So, the noise is covering the environment, we got that part. It's glowy and shiny, we got that too. However, the original effect is much more prominent than ours. Can you figure out why? How about from this angle? If we take a look at the effect in slow motion, we can see that while the effect is spreading across the environment, the rest of the environment gets darkened and loses a bit of color value. This helps emphasize the active part of the effect even more, driving the player's focus to it. Also, it increases the contrast between the dark areas and the glowy noise area. The implementation should be really simple. We're already sampling the original camera color, so we can easily adjust it. To darken the color, we just need to multiply it by a value lower than 1. And to have even more control of the effect, we can apply a different multiplier based on the luminosity of the original camera color. For example, we can multiply the brighter areas by a smaller multiplier than the darker ones so that we keep them more visible. To do that, we calculate the luminosity of the original camera color by multiplying its value by this constant. This constant is based on the sensitivity of the human eye to different color channels. Then, we use that luminosity value to determine the darkening multiplier. And here's how the effect looks when we darken the whole environment. Now the effect pattern gets even more exaggerated and it really pops out against the environment, just what we wanted. To emphasize it even more, we can also desaturate the camera color. This will make the whole environment look more uniform and bland, which will help to exaggerate the bright noise color even more. And here's the code that does just that. Once again, we calculate the luminosity of the camera color and then apply the desired amount of desaturation. The effect is really popping off now. It's bright and shiny, contrasting with the dark and desaturated environment. However, by increasing the contrast and visibility of the main part of the effect, the border of the effect is clearly visible now. It's really poking me in the eye. To smooth it out, I calculated the distance of a pixel from the edge. If the distance is less than some threshold value, it means that the pixel is inside the smoothing range. For these pixels, I mix the original camera color with the effect to provide a smooth transition, thus reducing the sharp edge of the effect. And here's how this looks in the scene. Here, I'm just visualizing the effect's influence on pixels, with white color representing the full influence. We can see that by tweaking the edge threshold and smoothness, we get a nicely smoothed out area around the edge. And if we take a look at how it looks with the effect, we get something like this. Nice. This small tweak really improved the look of the effect. Just look at the comparison with the previous state without the smoothing. However, while it's generally looking much better now, there's still something missing. Take a look at the original effect again and see if you can spot the missing part. It's extremely visible when casting the effect in an indoor environment. Did you see it? Let's watch this in slow motion. When the effect starts, the rest of the environment suddenly gets a slight bluish color overlay. However, this overlay is only visible on certain parts of the environment. It isn't uniformly applied everywhere. Well, it turns out that the parts of the environment that are facing the camera aren't covered with the overlay, while the other parts are. Even so, the larger the angle with the camera, the stronger the overlay. Whenever you notice this angle relation with the camera, you should immediately think of the Fresnel effect, since this is its base component. This effect is so common that Unity has a dedicated shader graph node for it. To apply it via code, I just calculated the angle between the normal vector and the camera by using the dot product. Then I've raised it to an exponent specified by an exposed parameter so that I could tweak its intensity from the editor. And here's how it looks in the scene. Notice how the overlay changes based on the direction the camera is facing. And this is how everything looks combined. By implementing the Fresnel effect, the visibility of the noise is reduced on surfaces directly facing the camera, which gives a much better insight into the details of the environment. In my opinion, this is a vital part of the effect. I mean, just look at the difference it makes from the previous state. Wow, this is amazing. Now, I'm really satisfied with the current look of the effect, at least in this static form. Let's bring it to life by animating its values over time. As always, let's analyze the original effect first. The effect starts by spreading from the player in all directions. At first, it's just visible 1 or 2 meters around the player. Then, it starts spreading out quickly before slowing down gradually and fully disappearing at the end. The whole effect lasts for about 2 seconds, which is apparently good enough for AC Valhalla, but not good enough for my girlfriend. To implement the animation, let's start with the scan range. This range represents the visible part of the effect. It starts at around 1 or 2 meters from the player and starts increasing rapidly. As time goes on, it slows down a bit but still continues to move across the environment. This is looking nice, but in the original effect, the noise disappears at the end of the effect by slowly fading out. This brings us to the second animated value, a global visibility parameter. At the start, the effect is fully visible and it starts slowly disappearing after a while. I've incorporated an easing function to provide it a more dynamic look while fading out. Next, let's animate the darkening and desaturation of the environment. It's quite similar to the scan range. Initially, there's no darkening of the environment. Then, as the effect starts spreading, the darkening gradually intensifies to the maximum value. Then, it stays there for a bit before slowly reducing back to 0. And here's how it looks compared with the previous state. This really pops out the main part of the effect. The next part is the Fresnel effect. Initially, there's no color overlay across the environment. Then, suddenly, in the first couple of frames of the effect, the Fresnel effect appears, increasing its intensity to the maximum value. It stays visible throughout the whole animation before fading out with the rest of the effect. And here's the comparison of the effect with and without Fresnel animation. The final thing I've noticed while examining the effect was that the color intensity of the effect increases at the start. It isn't immediately at full intensity. Instead, the intensity increases across a couple of initial frames, enhancing the feel of the effect bursting across the environment. Again, here's the comparison with the previous state. It's subtle but effective. The effect is really shaping up nicely. However, even with all these animated properties, it still feels a bit static in comparison with the original effect. Can you spot what gives the original effect that additional dynamic feel? How about from this angle? It turns out that the original effect has an additional movement of the noise throughout the whole animation. Also, while fading out, the noise looks like it's moving into the environment. This really provides that juicy feel to the final part of the effect. To move the noise, I need to update the UV coordinates that determine which part of the texture is being visualized. Moving them toward the scan origin looks like the noise was sucked toward the player, which looked fairly similar to the original effect. And let's see how it looks now in comparison to the previous state. It's subtle, but it gives a much nicer feeling when the noise starts disappearing, right? Like it's disappearing into the ground. I feel like we're so close to the final look of the effect, but the original effect just feels somehow more powerful than ours. Why is that? For this, I had to go in and examine the effect frame by frame, and what I found out was pretty surprising to me. It turns out that they're simulating camera shake by offsetting the whole effect in different directions for a couple of frames. I gotta say, I haven't noticed this anywhere else yet. This was a first for me. Luckily, implementing it should be an easy task. All that we have to do is offset the UV coordinates vertically or horizontally by the desired amount of pixels each frame. And we can get the size of the pixel through this special screen parameters variable. This variable holds the width and height of the render target into which the pipeline is currently rendering. And let's see it in action. Did you see it? The effect is really subtle, but it provides that additional intensity and power at the start. To feel the power even more, we definitely need to add sound effects. Unfortunately, I have no clue how to make engaging sound effects, so I just recorded the sound while playing the game and imported it into Unity. Let's see how much this means for the overall feel. And here's the comparison with the previous state. Oh, this feels so empty. With that, I think that the effect is fully recreated. Let me know in the comments below, what do you think? Is there something I overlooked? What could make this effect even better? By recreating the effect, I learned that the addictive feeling of effect doesn't come from beautiful visuals. Instead, it's achieved by adding many small incremental improvements that work together to make it really pop. And if you've learned something new from this video, make sure to subscribe as it would help us a lot with growing the channel. And that's it for this one. Thank you for your time and good luck with your projects.